I'm John Healy. This is joint work with Leland McInnes, who you saw give a dimension reduction talk earlier today. If you missed that talk, I'm going to highly recommend it. It was a lot of fun. When it goes up on YouTube, go check it out. I've got to give a quick shout out to another pair of colleagues here from the TUT, who are Shell and Amy Wooding, who are going to be giving a tutorial on reproducible data science tomorrow. I'd recommend you drop by that as well. So, who are we? We're mathematicians and researchers at the TUT Institute for Mathematics and Computing, which is a little research institute in Ottawa, Canada. We've recently been focusing some of our research efforts on sort of foundational mathematics underneath machine learning and data science techniques. To that end, a while back we came upon a great clustering algorithm called HDBSCAN. We figured out how to make it more efficient and developed it into an open source library that's now been contributed to scikit-learn-contrib. I'm going to talk to you a little bit today about both how and why HDBSCAN works. All right, to start with that, I'm going to roll back and talk about clustering in general. So let's get everyone on the same page. Clustering at its heart is about grouping together data points that are very similar. I'm going to break that down by breaking down clustering algorithms in a way that I find useful, and I'm going to apply Leland's sort of red star. This is going to be a very high level. I might lie a little bit in this breakdown, but I think it's going to give you the right intuition. So let's start off by dividing clustering algorithms into two sort of clumps. Clustering algorithms sort of naturally break apart into centroid-based or parametric clustering algorithms or density-based algorithms. So centroid-based algorithms are going to make explicit assumptions or implicit assumptions about the shape of your clusters. This is going to allow them to work on very small amounts of data very well, which is a really nice feature. Density-based clustering is going to allow your data to define the shape of your clusters. But it's going to require a lot more data to be very effective at working. So now we've got a nice break. Hold on, no, I got that wrong. We shouldn't break them down that way. That doesn't. The right way to break them down is flat versus hierarchical clustering. That's a way better way to divide it. Sorry. So this is about sort of complexity of resolution. Flat clustering gives you a single grouping or partitioning of your data, while hierarchical clustering returns sort of sets of nested relationships between your data, which is a much nicer way to think about clustering algorithms. No, those are orthogonal. All right, hold on. What if we got a two-dimensional partitioning of our clustering algorithms where we can have flat centroid-based, flat density-based, hierarchical centroid-based, and hierarchical density-based? That might be a nice way to group a nice taxonomy of clustering algorithms together. I'm going to give you a quick whirlwind tour through these four cells, starting with flat sort of centroid-based or parametric clustering algorithms. So these two of the most common algorithms in this space are k-means, which most people have probably heard of, or Gaussian mixture models. So as I mentioned, these have either an explicit or an implicit assumption about the shape of your clusters. So that's going to require you to have an a priori understanding of what you want your cluster shapes to be before you choose your algorithm. So this is going to work really well on small amounts of data. It's going to work in low dimensions where you can visualize your data and get an understanding for the shapes you're seeing within your data. But that's rarely a situation that I'm in. I often end up dealing with higher dimensional data where I can't see and don't know what my data really looks like. This is sort of the situation that I tend to find myself in. Higher dimensional versions of this, where my clusters form all sorts of different shapes, their variable densities, their variable sizes. K-means and parametric algorithms tend to perform poorly in these sorts of situations because they're going to make the Gaussian ball assumption. That is, your clusters are sort of high-dimensional spheres. Now, the Gaussian ball assumption, it's lovely in theory, but in my experience, it's a little bit like a spherical cow. Theoretically very appealing, but rarely occurring in nature. Additionally, they're going to make the same problem, have one problem, which is a number of clusters parameter or a resolution parameter that we're going to have to fit. And if we don't know a lot a priori about what's going on with the data, that's going to be really hard to set. All right, that brings us to flat density-based clustering. Examples here are DBSCAN or mean shift algorithm. These eliminate the parametric distribution assumption made by centroid-based methodologies, which is nice. Think of these as sort of non-parametric, data-driven versions of the centroid-based methods. DBSCAN, or let's see, density-based spatial clustering of algorithms with noise, applications with noise, sorry, is a popular density-based clustering algorithm. It's got some nice advantages. It's fast, it's robust to noise, it allows for variable shaped clusters. You get the nice advantage here. You notice all the points in the gray in the background? It's a clustering algorithm, not a partitioning algorithm, which means it's not requiring you to put every one of your points into one of your clusters, which is really nice if you think there might be actual noise in your data. K-means doesn't have that property, and you can get very variable clusters in high dimensions without realizing what's happening. Fortunately, it's got a similar disadvantage to our previous algorithm in that the resolution parameter on this is quite hard to set, which leads us to hierarchical centroid-based or parametric algorithms. And these are specifically designed to address that parameter selection problem. Since we don't know a priori what the correct numbers of clusters are, we're going to build a sort of a natural hierarchy over a whole range of our clustering and use that to try to divine the correct number. So that is often going to be represented as a dendrogram, which can be useful, but it can quickly overwhelm a user. So this is a picture of those clusters splitting up and breaking apart as it fragments down until you have every point in their own cluster right at the bottom. And so from this, you can sort of look at it and stir the tea leaves a little bit and say, oh, there should be 4, maybe 6, maybe 8 clusters. I know the answer I want, so I'm going to pretend that you can divine 6 from looking at this and say, ah, that's obvious. And that gives you this clustering. But again, we get hurt here by the parametric assumption implicit in what I'd used there, which was called ward clustering via hierarchical. And that assumption was essentially, again, the Gaussian ball. It's come back to bite us again. But everyone in this room at this point says, wait, John, you just told me how to deal with the Gaussian ball assumption. We'd use density-based clustering. And you would be right. So that would bring us to hierarchical density-based clustering. The big reveal there of the question marks to HDBSCAN shouldn't be a surprise to anyone who read the title of the talk before you came. So this is hierarchical density-based spatial clustering of applications with noise, HDBSCAN. This is the kind of space you want to use when you're using density-based clustering to robust to variable-shaped clustering, and hierarchical clustering to account for the resolution problem within your data. So HDBSCAN is a good example of a hierarchical density-based clustering algorithm. Let's talk a little bit more about that. Let's talk about hierarchical density-based clustering in general. So I'm going to start with a high-level motivating description that's going to give you an example of a natural way you might go about constructing a hierarchical density-based algorithm. All right, let's go back to that data set we were looking at before. This is DBSCAN. As I said before, the hard thing with DBSCAN is a slightly unintuitive parameter called epsilon. Finding the epsilon that's going to fit your data can be a little bit of work. So let's look what happens when we vary that epsilon parameter. For very small values of epsilon, we're going to get little tiny clusters and most of your data defined as noise in the background. We're going to increase epsilon. The background noise gets sucked into your clusters. Some of your clusters get merged together. We increase epsilon again. More background noise gets sucked in. Your clusters get over-merged, and eventually this will merge everything into one single massive cluster. This is easy to deal with if you're dealing with two-dimensional data. You can do the advanced eyeball exam, and you can say, I found the right parameter. I've looked at a lot of pretty pictures. In high-dimensional data, that gets a lot harder to do. But it turns out that as epsilon decreases, you've got to guarantee that components are only going to fragment into smaller clusters, are going to break into smaller clusters or vanish entirely. That's nice. That lets you build a hierarchical tree, which we could represent via dendrogram. And now we could stop here and say, ha, I have a hierarchical tree. This is what I present to users. I'm going to require you to do a cut through that tree, and I'm finished. Exercise to the reader, and I walk away. But that's still a bit too complex for my liking. It's a bit too complex to be useful, because these can get very, very complex for large data very quickly, and eventually look like a big mass of black on your screen. So what we're going to do is we're going to simplify that cluster tree. We're going to prune the dendrogram back by eliminating any clusters with less than min points in them. And this is going to get a much simpler dendrogram. And then we're going to use a cluster selection from this tree via either a flat cut, which we're sort of comfortable with from before, or via a more advanced technique that I'll talk about a little bit later. And that is going to give us the clustering that I wanted when I first looked at this data. So this is almost exactly what I wanted. The black points are noise again. The number of clusters looks about right. The clusters are nicely shaped. And the algorithm I just described is very roughly HDBSCAN. Now, why does density-based clustering work? So let's back up a moment and see what's going to go on. First, we should define what we want a hierarchical density-based algorithm to do. let's define a cluster. I'm going to define a cluster to mean a connected component of a level set of a probability density function of an underlying and unknown distribution over which our data samples are drawn. Obviously. What? Sorry. I'll back up and take that a little more slowly with some intuition. We're going to presume that's an underlying probability density function over which our samples of our data are drawn from. There's some areas that are less likely to see data. There are more areas that are more likely to have data drawn from them. You can color that with a heat map of that probability density function. Denser regions are more likely to see data showing up. Then I can draw contour plots over that, or level sets. And this is like a topography map. If you've ever seen one of those, you can see the level sets increasing as your areas get denser. We can take that, we can select a level set from that, cut it off. These look at the connected parts of those level sets and see what's close. In this case, we're going to call each connected part a cluster. That's going to result in our clustering. Everything not lassoed, I'm going to call background noise. Fine, I'm done. I have a great clustering algorithm. Except I don't quite. So what's the difference between what I just described and a clustering algorithm? First off, we don't know that probability density function that I drew initially. This is the underlying problem of density-based algorithms, is how you go about estimating that probability density function. Second, how did I choose that level set? A hint is carefully by hand knowing the answer I wanted ahead of time so that I can do a nice talk. In reality, this is the problem that the hierarchical component of our algorithm is going to try to deal with. Which level set should I choose? And lastly, we'd like an algorithm to be efficient. So we can do crazy things for hundreds or thousands of points, but if we want to scale to millions of points, we have to start talking about what we can do with good computational efficiency. And what I just described is naively not computationally efficient. So what can we do? If we know what we should be doing, let's see what's computationally feasible to do. All right. First, we're going to have to locally approximate that density. So there are two problems. Let's deal with the first one. So how are we going to do this in a fast, efficient way? And fast and efficient in this case means locally without looking at all of our data at any given point in time. All right, here's what HDBSCAN does. It's got two parameters, epsilon and min points. It's going to draw a bunch of balls of radius epsilon around all of our data. Then it's going to say, hey, if you have more than min points in your epsilon ball, I'm going to declare you dense. This is going to be very fast to compute. It's all very local, and it's point counting in very small local regions. Now, but what if we don't want a declaration of dense or not dense? What if instead we'd like an estimate of the density? Well, what if I draw circles of whatever radius would enclose min points, many points? And so now, in other words, what radius would I have to take before HDBSCAN declared a point to be dense? I'm going to draw those circles. I'm going to color code those circles, with smaller circles being darker, representing denser regions of space, lighter circles being larger, less dense regions of space. Now I'm going to take those colors, I'm going to map them on the points, and now what I have is a very fast to compute local point estimate of the probability density function at each of my points from my data set. So now we've done a fast way to compute the density. How are we going to compute the level sets? All right. The intuition here is that the connected components of a level sets are going to form a tree. So that's probably best seen with a pretty picture, maybe even an animation. Yes, it worked. So as your required density to be included drops, your background points start getting added into your clusters. And so as you encounter new branches, these things are going to merge together. You can think of this as the water level dropping and islands of your cluster appearing. And as they drop down, new islands will appear and other islands of your data will be merging together. At the base, when your density drops completely, all of the points are under a single massive cluster. All right, we can play the same game with our data points. You can picture slowly expanding circles around each of the data points as the density decreases. As the points become dense under the density, we're going to color them in, and we're going to merge circles when their components meet. You watch the tree form, and it's going to end in a single root. And that would be fine if we were dealing with Euclidean distance. The key point here is that we're not dealing with a pure Euclidean distance. We're dealing with something called mutual reachability distance within HDBSCAN. And all of that is saying that before you can connect two components, they don't have to only be close in Euclidean space, they also have to be dense. So we'd like to code both of those conditions into a single distance, and that's going to be mutual reachability distance. In this case, that's essentially writing a new distance function that's the max of the distance between the points, and each of their distance to their kth nearest neighbor. Their kappa is just distance to the kth nearest neighbor for a point. So this has the effect of pushing sparse points away from the rest of our data, but it's also what's going to make a flat cut through the tree we're going to build equivalent to running DBSCAN for a particular parameter epsilon. There's a little bit of a foreshadowing here. It turns out that this satisfies the triangle inequality, which will come up later in the talk and bring us great joy. Well, bring me great joy at the very least. All right, so now we've approximated the level sets of a tree. You might want to extract a flat clustering from that. Again, here's a dendrogram. We could do a flat cut across it. That would be equivalent to running DBSCAN for a given epsilon parameter. We could be done. But we would like to do something a little bit smarter. So we're going to do that condensed dendrogram again, and we're going to prune out any of those clusters of size less than min points. And the intuition here is that as the cluster is decaying, anytime a small 1 or 2 points, i.e. any point less than min points, or any number of them, fall out of a cluster, I'm just saying the cluster's shrinking. I'm not letting you spawn a new cluster. I'm not breaking off a singleton new cluster and a singleton new cluster. Clusters shrink unless they hit a point that splits them into 2 large chunks. And you get a much more simplified representation of the dendrogram coming out of that. Here, I've colored the dendrogram by the size of the cluster, and I've also done the width of those bars based on the size of the cluster, so you can see what's happening as those clusters fade away and then vanish. So now we need to select a clustering from this. A flat clustering would work, but we would like to find something a little bit more natural that's not going to force you to go and look at this dendrogram every time you want to find out the natural clustering. So what we're going to talk about is persistence of the clusters. So we want the clusters that live for a really long time in this density plot and are really large and have lots of our data. And that's going to amount to just maximizing the amount of ink we have on this page, subject to the constraint that if you select one of these clusters, you're not allowed to select any of their descendants. And we're done. You get a very natural clustering falling out immediately from that. And that's the clustering I showed you earlier, and that's HDBSCAN. So this is the HDBSCAN algorithm. It was described in a couple of papers by Campello, Mulavi, Sander, and Zivik. It's a great advance in clustering. I can't say enough good things about it. It should be amongst the first clustering algorithms I think anyone should run on their data. Unfortunately, even though it's a fantastic cutting-edge algorithm, it's n-squared, which could limit its applicability if you have large amounts of data. So what can we do? We could try to make it fast. All right, how are we going to go about making this fast? The key here is to realize that under the hood, this closely resembles a single linkage computation, which can be reduced to a minimal spanning tree computation. Prim's algorithm, one of the best algorithms around for computing minimal spanning trees. That's great, but it's only true when the number of edges is a small multiple of the number of vertices in your graph. Unfortunately, we have a complete graph with n-squared edges, and as a result, that's not going to be fast or efficient for this particular case. What other alternative algorithms do we have that we might make use of? So there's another algorithm called Boruvka's algorithm. So Boruvka's algorithm on a graph conceptually can be thought of as a parallel version of Prim's. So what we're going to do is we're going to start with all the vertices in their own separate components. And then for each component, we're going to find the shortest edge that touches that component that isn't in it, or in a component. We're going to merge those components. We're going to repeat over and over the process until we're left with a single component. And that single component is going to be the minimal spanning tree of your graph. The algorithm is E log V, which means we aren't doing any better than Prim so far. But, as I mentioned before, This isn't a general graph. We've got points in space. So this is a spatial graph. So what's Boruvka's algorithm look like on a spatial graph? All right, start with every point in its own component. We're going to query each point for its nearest neighbor that is not within the component. For each component, we'll add in the smallest edge, we'll merge, we'll rinse, we'll repeat, we'll end up with a single big component, and that will be the minimal spanning tree. It sounds like almost what I just said earlier, except I use a slightly different word. I said nearest neighbor, not shortest edge. So if we can find a way to speed up nearest neighbor computations, then we can speed up our whole algorithm, and we're good to go. Well, as everybody knows, if you want to speed up a nearest neighbor query, you look at spatial indexing trees. Fun. So the basic idea of a spatial indexing tree is that you're going to recursively partition your space into separate little regions, and then when you want to query a new point, you just drop it down your tree until you hit a leaf node. And then you only actually have to compare the distance of your new point to all of the points within the leaf node, because you've got bounds on the distance you can be away from any point within a given region. That's spatial indexing trees. They're well known. They do wonderful things for you. So now, the intuition we've just described has been put into practice by a great paper by Marchram and Gray. They actually provide us good complexity bounds. It's wonderful. It's called Dual Tree Boruvka for Minimal Euclidean Spanning Trees. Wonderful paper. It works for KD trees. It works for cover trees. That looks like a slightly complex complexity bound. Those C's are just really small data-dependent constants. The alpha is the inverse Ackermann function, which is if it takes on values between like 3 and 4 for any values in n ranging from 60 to 10 to the 80. So if you're clustering all of the data in the universe, it's maybe 4. Otherwise, it's a small constant, and you're okay. Make those vanish, and you're looking at an algorithm which is essentially n log n instead of n squared. Except that thing that came up last time again, mutual reachability distance, not Euclidean distance. But that's okay, because it turns out the only thing that they required for the algorithm to work was the triangle inequality holding. And we have the triangle inequality holding for mutual reachability distance. So with a little finagling and a fair amount of technical finesse, you can make the dual tree Boruvka algorithm work across mutual reachability distance instead of Euclidean distance. And we're good to go. So now we have an algorithm that theoretically works as n log n, and you're saying, sure, but those constants might be silly large and your algorithm could be garbage, and I'm sure it's vaporware. But no. So I ran experiments. So these are scaling experiments comparing the Python implementation of HDBSCAN that we have developed and is now in scikit-learn-contrib with the base implementation, Java implementation of HDBSCAN. Because we're comparing implementations as well as algorithms, you should take this with a giant grain of salt. Maybe a boulder of salt, because the details might not be in the algorithm, they might be in the actual details of efficient coding. That's okay. The only takeaway here is those lines are wildly different shapes. On the left you have sort of the natural timings, and on the right you have the log-log plots, and those shapes are very indicative of an n squared algorithm versus an n log n. So it looks like we've got a practical, efficient n log n algorithm running on our data. So you say, okay, well, you're faster than HDBSCAN, that's good, but I've got lots of other clustering algorithms I could use. How do you compare against those? That's an excellent question. Let's run that experiment as well. So these are grabbing a whole slew of the algorithms out of sklearn, and this is to minimize any sort of effect that might come from language-independent effects or base coding. Run a whole slew of them. You quickly see that this groups up into sort of 3 natural clumps of algorithms, the very fast ones at the bottom, medium speed ones, and the quite slow ones near the top. Let's throw out anything but the fastest ones, and then I can scale my number of data points out farther to the right, and we can see a more interesting comparison. So here, HDBSCAN is the dark green line. 2 k-means algorithms, scikit-learn and SciPy, are on the bottom lines. Yeah. And the interesting thing here is DBSCAN is the blue line. So that should be interesting because I had said earlier that running HDBSCAN is equivalent to running DBSCAN for every value of epsilon. That's DBSCAN run with a single value of epsilon, and we've managed to get it faster due to the computational tricks that we're using to speed things up. That's nice, but you should take that with a tiny grain of salt again, because DBSCAN's performance can vary wildly depending on the epsilon value you chose. It's a really good algorithm, it's very fast, it's very solid. If you pick epsilon too small, it declares every single one of your points as noise, and it's blindingly fast. It can do nothing really quickly. If you set epsilon too big, it grinds to a halt. Both of those cases are not fair to DBSCAN, which is a good algorithm. So if you want to compare against it, you need to find the right parameter that's doing something meaningful on your data to actually compare against. Okay. The way we got around that was we said, I'm going to do a massive hyperparameter search. I'm going to run HDBSCAN. I'm going to get a clustering. I'm going to get that persistent natural clustering extracted from the tree. Then I'm going to search across a whole slew of parameters for DBSCAN and find the clustering that best matched my HDBSCAN clustering. And that way I can guarantee that DBSCAN is doing something meaningful with my data. Once I found those, I'm going to plot the timings for those parameter runs against the timings for an HDBSCAN run. And the short takeaway here is the green line is HDBSCAN, the blue line is DBSCAN. They are performing very similarly. So you can get on meaningful runs with a single run of HDBSCAN all of the epsilon parameters of DBSCAN. And as a result, even if you like DBSCAN more than HDBSCAN, you want those flat cuts, the right way to go about doing it is to build the tree for every one of them and then choose the cut you want out of it. So there's not a reason to run DBSCAN anymore. If you want it, run HDBSCAN and pull the results out. So we've got an accelerated HDBSCAN. It's very easy to install. Reproducibility matters, so all of these experiments are available in notebooks or binders. You can load them up, you can run them, you can play with them yourselves. The interface, because it's in scikit-learn-contrib, you know the interface matches scikit-learn, which means if you've got notebooks or data analyses or anything like that that's making use of k-means clustering or hierarchical clustering or any of the clusterings out of scikit-learn, you can install this and swap out those algorithms for HDBSCAN immediately, look at the results, see what they do on your data. I encourage you to do that. If you like what you see or don't like what you see, give us a shout. We'll be very interested to hear your experiments and your experiences with the clustering on your data. Any questions?
If you go back and look at the metric that you choose.
Looked at which one?
The metric, the triangle inequality
yes.
metric.
You want this one?
Yes.
Mutual reachability distance.
Have you considered putting weights on the first two numbers or the last, or just the last one, and would that change anything? Like there's like a 5 in front of the D. Does that make sense? It would be weird, because yeah.
It would be weird. I would agree. Yeah. You would no longer be talking about density. You would be talking about some sort of different metric, right? Because this is all about trying to make sure that a point is dense as well as close, under DBSCAN's definition of density.
Yeah. So you change the definition of dense.
Exactly.
Yeah.
Yeah, but you could totally change the definition of density. That is very much a thing you could do.
Yeah. All right. Thanks.
No problem.
Anyone else?
You mentioned the triangle inequality a number of times.
Yep.
Could you define that?
Sure. If I am a particular distance away from if we are this distance apart, and Leland and I are this distance apart, I know that you two have to be closer to each other than going through this path. So if that doesn't hold, this is a basic definition of what we would call a metric space. You need this to hold for any of your intuitions to match up. It's faster to go to a direct route than to come off here and then go there. In any space that that holds, that's the triangle inequality holding. If that's not true, it breaks all of these sort of abilities to do those spatial trees that we were talking about. Does that make some sense?
Yeah, okay.
We could grab a whiteboard afterwards and I can grind through some more details if you'd like, though.
So algorithmically, if my data is larger than memory, what is the right way to build a minimum spanning tree? I'm not saying tools, I'm just saying how does one build the algorithm?
Right. My short answer is to buy a bigger computer. That was our solution. My longer answer would be to talk to a Dask developer somewhere and see if you could work together to get this built over top of Dask. I may have been pandering to the person who asked the question there. No. Yeah, it's hard, is the very short answer.
Okay, any more questions?
In your 2x2 ontology of clustering algorithms,
Sure.
where does spectral clustering fit in there?
Sure. So spectral clustering is flat parametric. So traditional spectral clustering is going to be done by inducing the nearest neighbor graph, looking at the Laplacian, doing an eigendecomposition, embedding that into a low-dimensional space, and then running k-means on that low-dimensional data. And so it's a spatial transform followed by a k-means. That's traditional spectral clustering. You could do something sneakier. So if you say, I'm willing to be spectral-ish clustering, you could embed that down into a low-dimensional space, and then you could run hierarchical clustering across it, or you could run something else on it, and that would move it out of that category. And this is sort of where dimension reduction and clustering start intersecting, which makes it a very natural thing to move from clustering research into UMAP research, which means you should go see Leland's talk on the web.
Thanks. What are your thoughts on using tsne as a method to make data more visualizable, either before or after using HDBSCAN?
My short answer is going to be I would suggest you use UMAP instead.
And what is UMAP again?
Uniform manifold approximation and projection.
Gotcha.
You can pip install UMAP. Easiest way to find that would be, if you want more details on it, Leland gave a SciPy talk on UMAP. My TSNE is a fine embedding technique. You can do TSNE and look at the clusters that come out. One of the issues I have had in practice with running TSNE before using HDBSCAN is the embeddings I get out of TSNE are very often unstable. So if I run the algorithm once and I run it again, I get different clustering out. And this typically makes my end users very uncomfortable, and it makes them less, they don't trust my clustering as much. And I don't want to inject any of that noise in it. I want very stable results. Gotcha. And so I really want a stable embedding technique before running a clustering algorithm.
Is it easy to explain the main difference between UMAP and TSNE?
No.
Okay.
But I will give you a pointer to the slides immediately afterwards.
Thank you.
It's not in the short time we have right now.
Okay, I think we have time for one more question if anyone has one. Okay, we can thank our speaker again.